of the conference in honor of Peter Swinnerton-Dyer. So I would like to remind you first, that the lectures are being recorded and live streamed. So please keep the, if you do not wish to be recorded, keep the cameras and microphones off, and it will continue being live streamed throughout the break. And I'm also supposed to remind you that live transcript can be turned off, or you can watch it if you see fit. And I would like to make a personal comment here. The live stream is particularly creative. So as Vladimir pointed out, my name was made into Sarah Zombies. Well, that is a new one. I have not seen that before. So, well, in any case, let us get started. So it is a great pleasure to welcome our first speaker, John Coates, who will tell us about classical Iwasawa theory and infinite descent on a family of abelian varieties.
Thank you, Sarah. Now, before I start the formal part of my lecture, I wanted to tell a couple of little stories about Peter. The first time I ever heard the name of Peter Swinnerton-Dyer and Brian Birch was in Canberra in 1966, shortly before I left to go to Europe to study for a postgraduate study. But I was in the library of the mathematics department in the institute side of the university, reading a book when Kurt Mahler, who had been the teacher who had got me interested in mathematics, he came up to me very excited and showed me this letter in German that he had got from Carl Ludwig Siegel. And Siegel had written to him, he explained to me that he'd written to him that he thought this 1965 paper of Brian and Peter, where they announced the conjecture, was one of the most important in number theory. And he urged me to read it. So, and I think in fact, the journal had only arrived very recently at Canberra. So that was the first time I ever heard of the name of Birch and Swinnerton-Dyer. And as I say, it was the great German mathematician Carl Ludwig Siegel who had been very excited by the paper. The second memory I have of Peter, which is a very vivid one, is that when I came to Cambridge after a year in Paris, and as a graduate student, even though he was very busy, he used to hold open house in his beautiful rooms in Trinity on a couple of nights a week. You could go along and have a drink around, I've forgotten, around 6 o'clock, before dinner. And it was a very interesting occasion. I wasn't Peter's graduate student or anything, but somehow I got to know about it. And they were nice occasions that he would talk a little bit about what he was doing, as well as all the university affairs he was caught up in. And I remember him talking at one point about more computations on the modularity of elliptic curves. But perhaps what was even more important was that he was, whenever there was a distinguished visitor who came to Cambridge in number theory, he would invite them along there, and he would go out of his way to tell you to come and have a drink with them. I remember that was the first time I met John Tate, for example. So Peter was extremely generous to people who were not his own research students at that time. And there was no one else doing that sort of thing in the department. Now, in my lecture today, I want to talk about some very elementary ideas that I have to explain in Iwasawa theory and their relevance for the conjecture of Birch and Swinnerton-Dyer for certain elliptic curves with complex multiplication. And the first thing that I just want to make, click to start the remote control, right, is that curiously, Peter, even though the p-adic methods of Iwasawa theory are, as far as we know today, the only general methods for attacking the conjecture of Birch and Swinnerton-Dyer, I have to say Peter himself was never very carried away with Iwasawa theory. He did do a little bit of work with Barry on the construction of p-adic L functions, but it was something which somehow he was always more interested in other questions in number theory. So now let me turn to the actual content of my lecture, and I have prepared this PDF file, and I'll try and add various comments as we go along. So what I want to explain is that if you look at primes congruent to 7 mod 16, we'll see why that condition is so important later, how very elementary methods in classical Iwasawa theory enable us to prove surprisingly strong results about infinite descent on the gross family of elliptic curves. I'll recall what this family is, with complex multiplication by the ring of integers of the field K, the imaginary quadratic field K equals Q adjoin the square root of minus Q. And the descent results are in perfect accord with the predictions of the conjecture of Birch and Swinnerton-Dyer. At the same time, they also prove some interesting phenomena related to a classical conjecture of Greenberg that I'll mention briefly. And in addition, they give a new proof of what I think must be about the oldest theorem, the last theorem of Helmut Hasse. So that's the general outline of what I want to talk about. And I should say immediately that everything I'm doing here is joint work with 2 young Chinese mathematicians called Li. One is Jianing Li, and the other is Yongxiong Li. So now, let me discuss the background. So in this first part of my lecture, I will basically be I will explain some results in classical Iwasawa theory, which are about fields. They don't have anything specific to do with elliptic curves. But then I'll explain that, in fact, they do after I've given the results. And the methods that let me stress that everything I'm going to do will use surprisingly elementary methods. I'll say something about them later on. Basically, it's class field theory and a little bit of the most basic facts of Iwasawa theory. So now the notation, as I've explained it there, I want Q from now on would denote a prime, which I always want to assume is congruent to 7 mod 8. And sometimes later I'll be assuming it's congruent to 7 mod 16. And I let K be the imaginary quadratic field Q adjoin square root of minus Q. It's all explained here in the text that's there. So OK will be the ring of integers of K, and H will be the class number of K. Now, of course, because Q is congruent to 7 mod 8, the prime 2 will split in K, and I'm going to write the 2 primes it splits into as P and P star. Now, by class field theory, K has a unique, so a Z2 extension of K, of course, is a Galois extension of K, whose Galois group over K is isomorphic to Z2, the 2 adic integers. And class field theory tells us that K has a unique Z2 extension, K infinity, which is unramified outside Gothic P, one of these primes. And of course, the Gothic P then will have to be totally ramified in it because the class number of K is odd because, of course, it's a field of prime discriminant. And similarly, K infinity star will be the unique Z2 extension of K, which is unramified outside the other prime, Gothic P star, lying above P. And then I will also write what I will call script K infinity, which is the composite of the two K infinity, compositum of the two fields, K infinity star. And it, of course, is a Galois extension of K with Galois group Z2 squared. And so it's the maximal, it's the composite of all Z2 expansions of K by class field theory. Now, in addition, I need a little bit of basic notation. I'll be interested in algebraic extensions of K, and I'm going to write L, if R is such an extension, L of R will be the maximal unramified Abelian 2 extension of R. It's the unramified one, the Hilbert class field. And MR will be the maximal Abelian 2 extension of R, which is unramified outside the primes of R, lying above P, Gothic P only. And similarly, M star R will be the maximal Abelian 2 extension of R, which is unramified outside the primes of R, lying above Gothic P star. And I'm going to use the notation now of R infinity will be the compositum of R and K infinity. So it's a Z2 extension of K. R infinity, which is unramified outside Gothic P. R infinity star will be RK infinity star. So it's a Z2 extension unramified outside Gothic P star. The primes above Gothic P star, of course. And script R infinity will be the compositum of R with the Z2 squared extension, which is curly K infinity. And now we define M of R to be the M of R, clearly, you see the extension R infinity over R, of course, is unramified outside Gothic P. So M of R, the maximal Abelian 2 extension of R, which is unramified outside Gothic P, will, of course, contain R infinity. And similarly, M star R will contain R infinity star. And so I'm now going to be interested in these three Galois groups here, the Galois group X of R, which is the Galois group of MR over R infinity, X star R, which is the Galois group of M star R over R infinity star, and YR, of course, which is going to be the Galois group of L of R over R. L of R, remember, is the maximal unramified extension of R. So this is our basic notation in what follows. And now I'm going to come very down to earth and introduce the polynomial f of x equals x to the fourth plus q. And now down to earth polynomial is hard to imagine. And now I want to introduce the following fields, namely, I want to take alpha, I fix any root of this polynomial f of x and call it alpha. And now I'm going to define f to be the field k adjoin alpha. F prime will be k adjoin alpha times the square root of -1, which of course is another root of f of x. D will be the field k adjoin the square root of -1. And J will be the field k adjoin alpha and the square root of -1. So it's obvious that J is the splitting field of this polynomial. And as a result, the primes, Gothic P and Gothic P star, will have entirely similar decomposition in J. Let me note also that D is Galois over Q, but that the fields, of course, J is Galois over Q, but the fields F and F prime are not Galois over Q, only being isomorphic extensions of Q. And it's not difficult to see that precisely one of the primes, P and P star, is ramified in F, and similarly in F star. And so I'm going to adopt the convention from now on that Gothic P is ramified in F, so that Gothic P star is then the unique prime of K above 2, which is ramified in F prime. So now, following classical ideas in Iwasawa theory, I'm going to define X of J infinity to be the Galois group of M of J infinity over J infinity. And X star of J infinity star will be the analogous thing with Gothic P replaced by Gothic P star, and of course J infinity replaced by J infinity star. And now the main theorem, which will tell us everything that we want, is this theorem 1.1, which tells me the following, that now I'm going to assume that I have a prime Q which is congruent to 7 mod 16. So of the primes congruent to 7 mod 8, half are congruent to 7 mod 16, and half are congruent to 15 mod 16. So I'm looking at the ones congruent to 7 mod 16. Then for such primes, we always have that M of F infinity is F infinity, and similarly M of F infinity prime star is the same as F infinity prime star. Moreover, and this is the thing that will really interest us, X of J infinity and X star of J infinity star are both free Z2 modules of rank 1. So in other words, X of F infinity is 0, and X of F infinity prime is 0, and the ones X of J, X star of F infinity prime, and X of J infinity and X star of J infinity are both free Z2 modules of rank 1. And I'll be explaining later in my lecture why this is the case using, as I say, very classical methods of Iwasawa theory. Now, I want to mention another theorem which follows rather easily from this. By the way, I should say, if anyone is interested, I'll only be sketching proofs in my lecture today, but if anyone is interested in the detailed proofs, I can send them. The paper has just been put online by the journal Selecta Mathematica. I can send you a copy of it. Now, the second theorem is the following. Well, first, let me remark that it's easy to see that for all the primes Q congruent to the 3 mod 4, the fields K, D, F, F prime, and J all have odd class number. They have no unramified Abelian Abelian extension, 2 or not. And now the second theorem is this theorem 1.2 here at the bottom, that for all primes Q congruent to 7 mod 16, none of the fields curly K infinity, curly D infinity, curly F infinity prime, and curly J infinity has a non-trivial unramified Abelian 2 extension. So remember these fields, let's just go back for a moment, please, to the, whoops, leave it like that. All of these fields have Galois group Z2 squared over the corresponding field with written with a Latin letter. Now, let me mention why this is interesting. Now, can we go on to the next page, please? Yeah. So that there is this beautiful conjecture of Ralph Greenberg's, which goes right back to his thesis, I think, which asserts that if you take any number field and you take the composite of all its, and any prime p, you take the composite of all its ZP extensions, then Greenberg's conjecture is that the P Hilbert, so the maximal unramified Abelian P extension of this composite of all the ZP extensions should always be pseudo-null as a module over the Iwasawa algebra. There's a very mysterious conjecture, of course, because it's saying that a module which intuitively could be quite much larger is always smaller than we expect. For example, for a totally real number field, assuming Leopold's conjecture, that would say that if you take the cyclotomic ZP extension of a totally real number field, then the P Hilbert class field of that should always be, the P Hilbert class field should always be finite, which we have no idea how to prove in general in that case. But at least here, this does prove this conjecture of Greenberg for K infinity, which is the composite of all Z2 extensions of K for the prime P equals 2. And it's one of the few cases in which we have a clear-cut result about this conjecture of Greenberg. So these are the two theorems in Iwasawa theory that I want to say something. Well, the second one I won't have time to say anything much about the proof, but the first one I want to discuss later, the ideas behind it. But let me say straight away that they depend on classical arguments from Iwasawa's theory, combined with the following result, which surprisingly can be proven by entirely elementary arguments. So if you remember the definition of the field F, it's it's the field that we get by joining a root of this polynomial x to the fourth plus q to k, then the group of global units of F will have rank 1. And I'm going to write eta for any generator of this group of global units modulo torsion. Of course, we don't have any explicit formula for this unit or anything like that, but what I can say is the following: if V is any prime of F lying above 2, I'm only interested in those, then log V of eta is, in fact, I claim, well-defined up to a sign. And by log V, I mean we take the V-adic logarithm applied to the group of units, the usual definition, in the completion FV of F at V. Now, also, I'm going to use odd V to denote the additive valuation on F of V, which is normalized so that the order of the local parameter at V is 1. Now, by our choice of notation, I recall that the prime P of K, Gothic P of K, is ramified in F, and the ramification index is 2. It's easy to see. And I'm going to write W for the unique prime of F above Gothic P. Now, the second remark, which is almost obvious too, these are interesting little exercises in algebraic number theory, is that when Q is congruent to 7 mod 16, the prime Gothic P star has inertial degree 2 in F. And so there's a unique, because F has degree 2 over K, there's a unique prime, which I'll write as W star of F above Gothic P star. And now, the previous theorems, in fact, all hinge upon the following elementary result. So we let eta be a fundamental unit of F, then provided Q is congruent to 7 mod 16, we always have that the order at W, that's the prime above Gothic P, of log W eta is 2. And the order at W star, the unique prime of F above Gothic P star, of log W star of eta is 3. And it will turn out, in fact, the first equality Yongxiang and Li and I discovered through much more highbrow arguments earlier, and then Jianing Li found a simple proof of 2, an elementary proof, and then he found the elementary proof of 3 that we give in this paper, of the second assertion. So, as I say, these are the basic facts in elementary Iwasawa theory. And now what I wanted to explain in the next part of my lecture is how they are connected with infinite descent on a family of H-dimensional Abelian varieties defined over K with complex multiplication. So let me recall that the Hilbert class field H of our imaginary quadratic field K is K adjoin the J invariant of O of K. This is the classical J function, classical modular function on lattices in the complex plane. Now, Dick Gross, I think in his thesis, showed that there's an interesting elliptic curve A defined over the field, actually the smaller field Q adjoin J of OK, with complex multiplication by OK and minimal discriminant minus Q cubed, and which has the additional property that it's a Q curve in the sense that it's isogynous to all of its conjugates. So as Gross remarked, I mean, these are in some sense, the simplest curves with complex multiplication by the ring of integers, the full ring of integers of this field OK. And in fact, one can, without too much difficulty, write down an explicit equation for A over Q of JOK, which Gross found and which I've given here. It's given by this equation y squared equals x cubed plus and so on there, where in fact m cubed is equal to J of OK, and R squared is this ratio of 12 cubed minus J of OK divided by Q when you choose to fix. Remember, these are going to be real numbers, so we fix the R to be positive in the second case to make a fixed choice, and there'll be unique real cube root in the first place. Of course, I'm using here a little bit of the theory of complex multiplication to know that there is such an M and an R in this field. And now, so this defines a curve defined over Q of J of OK, and therefore over H. And now what I want to do is we define B over K to be the H-dimensional Abelian variety, which is the restriction of scalars in the sense of V from H to K. So this is now an H-dimensional Abelian variety. And let me just recall the following basic properties of B, which were proven by Gross. So let me write now script B for the ring of K endomorphisms of B, and I'm going to write T, this curly T, for the with the tensor product of B over Q. And in fact, then it turns out that curly T is a CM field of degree H over K. So it's a complex multiplication field, a totally imaginary quadratic extension of a totally real field. And B, the endomorphism ring, is an order in this field T, which is not necessarily the maximal order. In fact, it's ramified over OK at precisely the primes dividing H, is one of the results of Gross. And in particular, since the class number H is odd, the primes Gothic P and Gothic P star are both unramified in this field T. Moreover, the torsion subgroup of BK is OK over 2OK, and so the action of this script B on this torsion subgroup gives an OK algebra surjection from curly B onto OK mod 2OK, whose kernel is the product of Q conjugate primes, because of course OK mod 2OK is the product of two fields F2, which I'm going to write as capital Gothic P and capital Gothic P star of B lying above P and P star. These primes are both unramified in B and have residue field also F2. Now, if F is any algebraic extension of K, the Tate-Shafarevich group B of B over F is, let me recall, is defined there, where V runs over all the non-Archimedean places of F, and as usual, FV denotes the completion at V of the finite extensions of K, the union of the completion. So it's a torsion B module, and I'm going to write SHA B over JP for its pre-primary subgroup. By the way, we could extend, of course, well, I'll say a little more about that. I mean, essentially the Tate-Shafarevich group of B over H is the same, let me remark in passing, as the Tate-Shafarevich group of the B over K is the same as the Tate-Shafarevich group of A over H, because one comes from the other. The representations, the local representations are just the induced representations. Now let's also mention that if we look at the points of B of F and we tensor them with Q, they will have a natural action of this field T, and thus, since T has dimension 2H over Q, the Q dimension of this field will always be a multiple of 2H, which is the Q dimension of Gothic T. So that will be important in what follows. Now, it's not difficult to see. I mean, in fact, this is done in a slightly earlier paper of Yongxiong Li and myself in most of this, the relation. You see, the field J infinity is in fact K adjoin the square root of -1 and B adjoin the Gothic, capital Gothic P infinity division points on B. And similarly, J infinity star is the field K adjoin the square root of -1 and B Gothic P infinity star. This is not very difficult to see at all. And as a result of this, it's very easy to translate the theorem 1.1 has the following entirely equivalent formulation in terms of the Abelian variety B. Namely, you see the Selma group of the Gothic P infinity Selma group, the capital Gothic P infinity Selma group of B over J infinity is very is essentially the x of j infinity and similarly j infinity star. So what it tells you immediately, the slight details needed to explain this are given in the paper that I mentioned, is the following equivalent form of theorem 1.1. So assume Q is a prime congruent to 7 mod 16, then either the points of bj infinity tensored with Q and bj infinity star tensored with Q have dimension 2h as a Q vector space, and SHA, the Gothic P, capital Gothic P infinity part of the SHA is 0, and similarly there should be B, that should have a Gothic P star on it there. They should both be 0, or alternatively, these mod LV groups, when tensored with Q, is 0, and both of the parts of the corresponding parts of the SHA, I'm sorry, this should be Gothic, capital Gothic P star there, are both isomorphic to Q2 mod Z2 as Abelian groups. So this is a direct translation of theorem 2.1. And I'm not going to, it's more an exercise than anything else. In fact, one can show by a purely arithmetic argument that's explained in the paper which I mentioned of the three of us, that a stronger form of theorem 2.1, namely, let's now look at the field D, which is K adjoint square root infinity minus 1, so that J infinity over D infinity and J infinity star over D infinity star are both quadratic extensions. Then the equivalent form is that provided the prime is congruent to 7 mod 16, then either BD infinity tensored Q and BD star infinity, these smaller fields, have dimension 2h as Q vector spaces, and the SHAs, the Gothic, capital Gothic P parts of the SHAs are both 0, except this should be Gothic, capital Gothic P star here, or else the alternative is that both of the mod LV groups are 0 when tensored with Q, and these Gothic, these parts of the SHA are Q2 mod Z2 as Abelian groups. So in effect, I mean, theorem 2.1 and theorem 2.2 have done the infinite descent on, which is usually very difficult to do, where they have come from completely determining the Selma group, the Gothic P infinity Selma group over the fields J infinity and D infinity, and the Gothic P star infinity Selma group over that. So it is surprising that one can completely determine it by these rather elementary methods that I'll be talking about later. Now, I should say that you can go no further without bringing in L functions, without, in some sense, proving something related to Birch and Swinnerton-Dyer. And in fact, in our paper, we show, using by slightly strengthening an analytic argument due originally to Miller and Yang, that if we write LB over DS for the complex L series of B over D, then in fact, theorem 2.3 there is true that for all primes Q congruent to 7 mod 8, LB over DS has a 0 as S equals 1 of exact order 2H. And as a result, by the work of Hegner and Gross and Zagier, the fields, the rational points BD tensor ZQ do have dimension 2H as a Q vector space, and the SHA of B over D is finite. So this is using analytic arguments. You have to say a tiny bit more than Miller and Yang, because I think their argument would only prove this for the primes Q congruent to 7 mod 8, which are sufficiently large. But by slightly reworking their argument, you can do it for all of them. So if you combine that with the earlier result, you get this stronger assertion here at the bottom, namely that BD tensor Q and BD infinity tensor Q and PJ infinity tensor Q, they're all Q vector spaces dimension 2H. In other words, you don't acquire any more points of infinite order as you go up these Z2 extensions. And similarly, SHA of B over D infinity P is the same as SHA of B over J infinity Gothic P is 0. And similarly for the D infinity star and J infinity star. Now, time is moving on. I want to at least try and say a little bit about the proofs. And so let me now move on. So the first thing I want to talk about is two very elementary lemmas about the decomposition of primes in the fields K infinity and K infinity star. And these two elementary but curious lemmas play a crucial role in the proof. So let me write Gothic Q now for the unique prime of K lying above Q. And I'm going to write Kn for the nth layer of the Z2 extension of K infinity over K. And we have these two lemmas here. So the first one tells us how the prime Gothic Q, which of course is unramified in K infinity over K, how it decomposes in K infinity. And of course, there's a parallel lemma for K infinity star. And the lemma is the following: let RQ be 2 to the power, the order at 2 of Q plus 1 minus 3. Then the claim is there are exactly RQ primes of K infinity lying above Gothic Q. In particular, there's one if Latin Q is congruent to 7 mod 16, and Q will split in K1 already when Q is congruent to 15 mod 16. So this is not very difficult to prove, granted the fact that we know that how to write the K in terms of the Ray class fields modulo small Gothic P to the n and Gothic P star to the n. But the second one, which is curious and which I want to say a little bit about, is nowhere in the literature, is the following: that the prime P star, which I recall is unramified in K infinity by definition, it will be inert when Q is congruent to 7 mod 16, and it will split in K1 when Q is congruent to 15 mod 16. So this is the fundamental difference between the two cases. So let me quickly say a little bit about the proof. You take the composite of the two Z2 extensions of K, which is curly K there, and I'm going to it's curly K infinity. I'm going to let curly K be the first layer of this extension of the Z2. So its Galois group over K is Z2 cross Z2. And then you see immediately that this should be, lemma 3.2 is equivalent to saying that there are 2 primes of this field, Gothic K here, lying above 2 when Q is congruent to 7 mod 16, and there are 4 primes of Gothic K lying above 2 when Q is congruent to 15 mod 16. So why is this the case? Well, let's make the following observation. K contains the first layer k square root of 2 of the cyclotomic Z2 extension of K. Naturally, because I mean all Z2 extensions of K are contained in K infinity, and so the first layer will be contained in this Gothic K. And so this means also that the field, which I've written here as Gothic M, which is Q adjoin the square root of minus 2Q, will be a subfield of Gothic K. And now I leave it to you to check that the extension Gothic M square root of 2 over Gothic M is unramified. That's very easily checked. And moreover, the extension K from Gothic K from M over square root of 2, I'm here in the proof, is unramified because Gothic K is K1 adjoin M to M over the square root of 2, or K1 star M over square root of 2. And since there can be no common ramification between K1 and K1 star, we get what we want. So we get that K over M is an unramified cyclic extension of degree 4. And now so if I look at this field M, there will be unique primes of M lying above 2 and Q, and I'm going to denote them by Gothic R and Gothic S respectively. And of course, the product of these two primes will be the principal ideal, the square root of minus 2Q, so that they have the same residue degree in the unramified extension by class field theory, K of M. And the point is that Q splits in Q adjoin the square root of 2, as you check immediately, so that there are two primes of M adjoin the square root of 2 above S, both with residue degree 1. And as K is K1M, it follows that from lemma 3, now we use, so it all boils down to now that the decomposition of R will be given, of this prime R above 2, will be given by the decomposition of Q. So now we just invoke the previous lemma, which tells us that Q is inert in K1 in particular, when Q is congruent to 7 mod 16, and splits in K1 when Q is congruent to 15 mod 16. And so this tells us exactly what we want, that there'll be two primes above 2 in this field, this composite of the Z2 extensions of K, when Q is congruent to 7 mod 16 and 4 when Q is congruent to 15 mod 16. Now time is running out, so let me just say that this it's just a tiny little exercise to deduce from this classical theorem of Hasse, which I believe is his last published theorem. It was published about 1969. And he looks at the field Q adjoin the square root of minus 2Q and proves that 4 exactly divides the class number of M when Q is congruent to 7 mod 16. We've shown that 4 always divides the class number, but exactly divides it and that at least 8 divides the class number of M when Q is congruent to 15 mod 16. So that's I'll leave it to you as a nice little exercise if you're interested to prove Hasse's theorem. Now I have to try and explain the second ingredient rapidly in the proof of theorem 1.1. And it's a class field theoretic analytic class number formula, which in this case of split primes was first established for odd primes in my old 1977 paper with Andrew Wiles on the proof of Kummer's criterion for Hurwitz numbers. But now it's completely general. I wanted to state it. It's got nothing to do with the prime 2. It works for all split primes. So K will now be an all imaginary quadratic fields, an arbitrary imaginary quadratic field. P will be an arbitrary prime number, which and P, Gothic P will be any prime of K such that KP equals QP. So P is going to split in K and there'll be two primes above it. And F will denote an arbitrary finite extension of K. I'm going to write S for the set of primes of F lying above Gothic P, D for the degree of F over K, H of F now for the class number of F, and omega F for the number of roots of unity in F. And now I'm going to let M of F be the maximal Abelian P extension of F, which is unramified outside S. Remember, S consists of the primes above Gothic P. So this is like the field that we were thinking about earlier, but in a much more general setting. And F infinity will be the field, the composite of F and K infinity. So it will obviously be a subfield of MF. And of course, K infinity will be the unique ZP extension of K unramified outside F. Now I let epsilon 1 to epsilon D minus 1 be a basis of the group of global units of F and modulo torsion. I'm going to pick a fixed algebraic closure of KP equals QP, and I'm going to write phi 1 through to phi D for the distinct embeddings of F into KP. And then I'm going to define the Gothic p-adic log regulator of F. Log Gothic P will denote the p-adic logarithm function on KP bar. In the usual fashion, I take D of the embeddings and I take the determinant of the log Gothic P phi epsilon J that we have there. Of course, it's always conjectured to be non-zero. It's a variant of the Leopold conjecture, but we only know it when F is Abelian over K. And now let me write delta P be any generator of the Gothic P component of the relative discriminant of F over K. I'm going to write NV for the absolute norm of an ideal V of F, and the integers E and F are defined by F intersect K infinity will be KE, and H, the Hilbert class field of X, intersect K infinity will be KF. Then the theorem is this one here. So under these general conditions, the degree of MF over F infinity is finite if and only if the p-adic regulator of F P is non-zero. That's immediate from class field theory. But what requires an interesting little exercise is the statement here that if the p-adic regulator is non-zero, then the degree of MF over F infinity is given by this expression here, namely the class number times the regulator over the square root of the discriminant times the number of roots of unity. And then there is this little additional factor here, which is coming in. And then, of course, here we have the what you'd expect from, these are the Euler factors at the primes in S corresponding to the point S equals 1. So in fact, this purely class field theoretic theorem, I'm sorry, I'll follow in, end in just one moment. It's a pure exercise in class field theory, which I had first worked out for totally real number fields. And in that case where we know the main conjecture, it's entirely equivalent in the end for proving, it proves the Leopold's p-adic residue formula for an arbitrary totally real number field if you use the full Wiles's proof of the main conjecture in general, but that Kohlmeyer's actually proved directly anyway later on. But here we don't know the main conjecture for arbitrary finite extensions of K, F of K, but it does give, I think it's essentially known for the Abelian extensions of K, but again, I doubt if it's ever been written down for the primes dividing 2. But in any case, it's some variant of Leopold's p-adic residue formula. And it's the first hint in global class field theory of Iwasawa main conjectures. Now, I had hoped to say a little bit more about the proofs, but I don't have time. But there is one other comment that I'd also wanted to make, that what we know so far about the conjecture of Birch and Swinnerton-Dyer is we know that for when the order of the zero is at most 1, or in these cases like in the gross curve situation, it can be up to 2h. It has to be a multiple of 2h. We know that if the L function has a 0 of the right order, which is of order 1 usually, then in fact, let's forget about that situation. Let's say of order 1, then the Tate-Shafarevich group is finite and the rank is the same as the order of the 0. But what we know for practically no elliptic curves at all is that in the Birch-Swinnerton-Dyer conjecture, there is this beautiful exact formula for the order of the Tate-Shafarevich group, assuming it's finite, which of course we always believe to be true. But we know it in practically, there's only just a tiny little handful of elliptic curves with complex multiplication in which the full order has ever been proven. And I think it's one of the, numerically, of course, there's been quite a lot of work done, which I had hoped to talk about, showing that everything looks beautifully true for this formula, in particular in this CM gross curves that I was talking about and so on. But the detailed proof of the order of the Birch-Swinnerton-Dyer of the Tate-Shafarevich group has only been written down for certainly in general, sometimes all but a finite number of primes p, but often an infinite number of missing. And it's really a very interesting problem that we end there to saying, to prove this beautiful formula of Birch and Swinnerton-Dyer for a much wider class of elliptic curves over Q and elliptic curves with complex multiplication. Thank you very much for your attention. So I'll finish here. Sarah.
Yes, thank you very much for this lovely talk. Are there any questions?
May I ask something, please?
Yes.
So this is John Cremona. This is about your final remarks. William Stein's student, Robert Miller, I think, clarified the exact formula for the order of the Tate-Shafarevich group for many elliptic curves of rank 0 and 1. I think certainly all the ones that conduct up to 1,000, maybe further.
Whose work is that, John?
Robert Miller.
Ah, I see.
About 10 years ago. He has since left mathematics, but their paper is published, and he goes into great detail to make sure that he gets the right order at every single prime. Some of the cases were quite difficult when there was a curves with a 7 isogeny, and because it's then the 7.
And he dealt with the prime p equals 2.
As far as I remember, yes. As far as I remember, it was exactly for all primes. But for really quite a lot of elliptic curves.
Right. Of course, I was thinking, John, more of general theorems.
Ah, yes. No. This is not general. Well, he's applying general theorems to special cases by doing computations.
Right.
Okay. Sorry.
Oh, yeah, I have a small question. Yeah, this is Henri.
Yes. Yeah, I know it's you, Henri.
Okay. Yeah, I was wondering when you said that the Mordell-Weil rank is positive, and there you seem to invoke the full force of Gros-Zagier. Is it possible that to get by maybe by a more elementary approach, by making some kind of two descent, for example? I mean, I'm wondering whether it would be conceivable that one could show directly that the Heegner point is not divisible by 2 or something like that.
I have no idea, Henri. It's not. I mean, the two. I mean, you know, we do the two descent, the Gothic P infinity descent, and all it tells one is there's either this copy of Q2 mod Z2 in Shah, or there's this copy of Q2 mod Z2 coming from the Mordell-Weil group.
Mhm.
I have no idea how to separate the two. If you do, I would be delighted.
I mean, there have been calculations like that in the past by Maser and so on, where one looks directly at the Heegner point and tries to show it's of infinite order without calculating its height and using the relation with L derivatives. But
Yeah, well, I don't know. I mean, I'd be delighted if someone can do that. Although, as I say, it's only a slight modification of the Miller-Yang arguments that we give in our paper to get at least get the zero is of the exact order and then invoke Gross-Zagier. Yeah.
Mm-hmm. Are there any further questions? Are there any further questions for John?
I have one, if that's okay. Your elegant and very elementary methods for the computation of the Selmer group and the Iwasawa two-adic setup. You do it for the gross CM elliptic curve. I assume you're also going to be thinking of more general CM setups?
Well, yes. I mean, there is a family. Which Yongxiong and Li and I discuss where the L function. You see, I mean, we want a curves Barry for which we know a priori that there are no extra points when you go up this Z2 extension. And now there is a large family of twists in that. We have a paper, Yongxiong and I, in the published in the London Mathematical Society a few months back, where there is a large family of quadratic twists of those curves where that property holds. So I think in principle, one should be able to extend the arguments to that sort of situation. The only thing which I'm not so sure about is this business about computing the trace of these of the fundamental unit of the field F.
Oh, yeah.
Down to of the logarithm of that. Whether you can do that for that larger infinite family, I don't know. I wouldn't be surprised that Yongxiong Li was able to do it, but it's an interesting question, Barry. But there is at least one family where which they are all quadratic twists of the gross curve, where there is a potential for doing that. Yeah.
Beautiful talk, John. Thanks.
Thank you, Barry.
Are there any further questions for John? Well, if not, then I suggest that we thank the speaker again.
Thank you.
Right, and we will meet again in 11 minutes for the second talk.